Now that we know what a subspace is, we're going to look at some examples of subspaces of our more known vector spaces. So just to remind you, for a subset of a vector space to be a subspace, it must be a vector space itself. And we saw the way we show that is firstly just to make sure that it's non-empty, and that it's a subset of that set. It's non-empty is the first thing we want to show. The second thing we want to show is that set is closed under vector addition. And the last thing we want to show is that set is closed under scalar multiplication. So let's look at some sets we know. Let's start with R2. R2 we already saw in the first video in this section of subspaces that lines through the origin form a subspace of R2. And then the two obvious ones, the whole set of R2 and the set with just the zero vector, which is the ordered pair 0, 0. Subspaces of R3, the obvious two, the whole of R3 and the zero vector. But then also planes through the origin, which takes on this format for A, B, and C, a real number, and lines through the origin, which takes on this format where T is a real number. So for example, if I've got the set 3x, 3y, 3z, that represents a line through the origin where x, y, and z are real numbers. So that will be a subspace of R3. So these are all subspaces of R3. Just a word of warning, R2 and R3, there's no relationship between the two in terms of subsets. The one is not a subset of the other because elements of R2 are ordered pairs. Elements of R3 are ordered triplets. So there's no relationship between the two. So the one is not a subspace of the other one. Do not get confused with that. All right. So let's look at square matrices, M, N by N matrices. Firstly, symmetric N by N matrices forms a subspace. Let's look at the case of 2 by 2 matrices. If I've got symmetric 2 by 2 matrices, A, B, what makes it symmetric? Those entries are the same. So if A, B, and C are real numbers, this set is a subset of M22 of all 2 by 2 matrices. It is non-empty because 0, 0, 0, 0 is in there. You can choose any two elements from this set, and if I add them together, these entries are going to be the same again. And if I multiply any entry from any element of the set with any scalar, those entries are going to be the same again. So it's closed under vector addition and scalar multiplication. Upper and lower triangular matrices and diagonal matrices are all subspaces. So let's just look at the triangular matrices in terms of our M22. A triangular matrix, A, B, and C, there's a 0 either in the upper or the lower triangle. So where A, B, and C are real numbers, if that's what my matrices look like, they take on this form. The significant entry is the 0 over there. That's also a subset of M22. It's non-empty because the 0 matrix is in there. But also if I take two elements from there, add them together, I'm going to still have a 0 there. Or multiply an element with a scalar, I'm still going to have a 0 there. Similarly with diagonal matrices. Diagonal matrices, if I just look at, and these are just 2 by 2 examples, it could be any square matrix. A, B, both those entries are 0. That's a subset of M22. It is non-empty. It's closed under scalar multiplication and vector addition. And you can test all of that. Right, now here's something to take note of. Invertible square matrices is not a subspace of M in N, of square matrices. Meaning if I've got two invertible matrices, I'll show you an example of 2 by 2 matrices. I can find two matrices, 2 by 2 matrices that are invertible. But if I add them together, I do not get an invertible matrix. For example, 1, 1, 2, 3. This matrix is invertible. How do I know that? The determinant is non-zero. -1, -1, 3, 4. Also invertible because the determinant is non-zero. But if I add them together, I get 0, 0, 5, 7. Row of zeros, determinant is 0. This is not an invertible matrix. So if I've got the set of all invertible matrices, it is not a subspace of the set of all square matrices, whatever the size is, because it's not closed under vector addition. All right, and just some more common subspaces. We're not going to prove these, but just to mention for completeness, if I look at the set of all functions from minus infinity to infinity, if I look at the set of all functions, the set of all continuous functions on that interval is a subspace of f minus infinity, infinity. The set of all continuous functions with continuous derivatives, the set of all continuous functions with the nth derivative being continuous. So we carry on. Those are all subspaces of the functions. All right, and if I look at the polynomial functions, the set of all polynomial functions, p infinity, if I've got the set of all polynomials where the degree is equal to n, that is not a subspace of all functions. And we showed that that is not a vector space. If you look back to this section we did on vectors, real vector spaces, we show that that's not a vector space. But if I look at degrees less than or equal to n, that is again a subspace and a vector space in its own right. And that's denoted Pn. So if I've got a known vector space and I've got a subset, so if I've got a known vector space V, I know it's a vector space, and I've got some set that's a subset of that set V. If I use the same vector addition or scalar multiplication, it's much easier to show that W is a vector space. Because we need to show simply that it's a subspace, so that it's non-empty subset closed under vector addition and scalar multiplication. So we do not have to check all 10 the axioms if I already know my set V is a vector space.